next talk. So our next speaker will be Dr. Bettina Heim from Microsoft, and she will talk on quantum intermediate representation. So Bettina, please.
Thank you very much, and thank you all for joining me here. So when we think about quantum computing, we're not short on ideas about all the possibilities that it can offer. From material discovery to traffic optimization, quantum computing promises a fundamentally different set of tools with which we can potentially solve problems in a wide range of domains, and hopefully better than we can do today with other means of computing. But as promising as quantum computing is, we still have a bit of work ahead of us before we can leverage it for applications at industry scale. If we look at pictures like these, they look awfully similar to the pictures from the early days of computing, like these, for example. The first programmable electronic general purpose digital computer, ENIAC, here, for example, could perform about 5,000 operations per second. And people were, interestingly enough, pessimistic about its ability to scale. Today's supercomputer, on the other hand, can perform a couple of hundred petaflops per second. So computing really has come a long way since these early efforts. While transistors still look like this, today we have about 7 billion transistors in gaming consoles, for example. So the question really is, how did we get from this to this? More than just advances in transistor fabrication, there's a lot that made classical computing as we know it today possible. So the question is, what will be required to bring quantum computing into the era of modern computing, so to speak? Fundamentally, leveraging a computer requires us to translate our ideas into instructions that a computer can understand. And today we are used that this looks something like this. Modern programming languages, in a sense, try to be close to how we would explain a program to another person, since this is what's most understandable to us as humans. So programming languages are supposed to make it easy to capture the essence of an algorithm or of a program. However, if we think about how to execute a program on quantum hardware, then the current reality is that what the quantum processor understands is much closer to something like this, which is the same program as the one on the right for 3 qubits. Now here it's much less obvious just looking at the code to know what it is supposed to accomplish. Imagine having to build, debug, and maintain millions of lines of code like this. And indeed, this is exactly what we did in the early days of computing. Code back then didn't look much different. However, programming languages have evolved significantly since then, and the job of a compiler is to translate between what's most understandable to us as humans into a representation that enables efficient execution. Clearly, there are many steps between how we would describe an algorithm to another person versus the instructions that we would give to a quantum processor. When we describe a quantum algorithm to another person, we would say something like, do a reflection or do a rotation. However, taking things like finite precision or geometry of the device into account, the same logic, the same rotation may be translated into a different sequence of instructions for the quantum processor, depending on the execution context. Depending on whether I execute a rotation once or a million times, I may have to choose a different precision when we're approximating that rotation. Now, if we write a library, for example, then we don't know the execution context ahead of time. Only the compiler, once it gets the whole program, can determine that. So if we don't intend to write a separate program for each problem instance and targeted hardware, then we need a certain amount of automation for these things. So to enter the era of modern quantum computing, as I phrased it, we need to think about the bigger picture, about how everything fits together. If we assume that there's not a single person or a small group of people that are experts in all of those pieces, then building a software stack that allows us to share and leverage all of our knowledge for different parts of the stack and across different domains becomes vital for quantum computing to succeed. So we need more than quantum hardware. We also need to leverage the power that classical computing has to offer and all the insights into how classical computing has evolved over the course of the last couple of decades. And we need the ingenuity that people can offer. Ultimately, we all bring our unique set of skills, our insights, our ideas, our perspective, and our vision. So we need those unique assets that each one of us can contribute to solve the world's greatest challenges. If we look at computers today, they in many cases can do far more than a single human can do. And part of the reason for that are modern programming languages. Programming languages are the bridges that allow us to share and leverage our collective knowledge. So they're vital for us to succeed. And this is exactly what we set out to achieve with Q#, to bridge our gaps in knowledge and connect all the pieces. So quantum computing offers exciting promises regarding how we can benefit society. However, if we think about quantum today, in many ways, today's environment is similar to the state of classical computing in the early 1950s, meaning each system is different and capabilities and resources are highly limited. We face several major technical challenges throughout the stack that yet need to be overcome in order to fulfill that promise. It is not yet obvious which hardware technologies are likely to succeed and which applications will ultimately benefit society. So to advance the field of quantum computing, we need to think beyond just how to build a particular end-to-end system. We need to think about how to make it possible to easily connect emerging technologies. We need to think about how to grow a global ecosystem that facilitates to develop and experiment with different approaches. And this is what we want to accomplish with Azure Quantum. In Azure Quantum, we support execution on a diverse set of backends from different quantum hardware providers. So the question more broadly for us is, how do we effectively connect a variety of different front and backends? Now, there are a couple of different execution models that one could imagine for quantum. In general, one might expect, however, that there is a certain amount of compilation and optimization that will be done purely statically. That there's a certain compilation steps that will have to be done just in time, right before execution, such that classical expressions can be evaluated before generating the instruction sequence that is to be sent to the quantum processor. And that there are certain things that will be handled by the runtime, such as error correction, for example. By and large, we can distinguish 3 stages during compilation. A part that is language specific, followed by a set of compilation passes that are language and mostly target independent, up to some basic information about the intended backend, such as, for example, the exact instruction set that it supports. And finally, things that need to be implemented for each execution target specifically. By defining a common format for these passes that are independent on the language and targeted backend, we can decouple the development of these pieces. So being able to advance different parts of the stack concurrently allows for a certain co-development of hardware, software, and applications. The question for us is how to achieve a certain modularity and pluggability while preserving all the benefits of a tight integration. To answer that, let's look at roughly how a program gets translated into instructions for the quantum device. We start with a piece of code that is translated by the compiler into an intermediate format based on which an executable is built for a specific target. And during execution, the instruction sequence for the quantum processor is generated and executed. Now I'll omit a couple of lower levels of the stack. Let's think about that instruction sequence for the quantum processor. So if the instruction sequence for the entire program can be determined without knowing any of the measurement outcomes, then things are relatively straightforward. But for more involved applications, this may not be possible, such that a repeated communication basically between the runtime and the processor is needed. A common interface between different front and backends hence needs to be able to represent classical computations in addition to the quantum pieces of the computation, if we indeed want to support that scenario. And we've recently made a first draft public with a specification for a quantum intermediate representation that serves precisely this purpose. So what is this quantum intermediate representation, or QIR for short? Now, QIR is a language and hardware agnostic format within the LLVM IR, meaning it defines how quantum programs are represented within LLVM. This, of course, prompts the question, well, what is LLVM? And LLVM is a mature open source compiler framework that is widely used in classical computing. The latest research in compiler research, for example, often comes with an implementation contributing or at least extending the LLVM framework. So you might wonder why we chose a representation within that framework, the classical framework, rather than a custom format. Well, for one, at the IR level, what we need for quantum is not that different than the tools that are needed for classical compilation. Leveraging LLVM toolchain grants us access to an arsenal of existing mature tools, such as for dependency management and tracking, to emit human-readable formats or to get a binary representation. These are all tools that have nothing to do with specific quantum capabilities, and if we went with a custom format, we would just recreate them from scratch in much the same way as they already exist. Additionally, the LLVM IR has exactly the same purpose of serving as a common format across multiple front ends and backends. The idea is that each language supports compiling into that intermediate format, and each execution target is capable of consuming it. And this hence saves the trouble of having to build an end-to-end compiler for each combination of language and target. And with that idea, many classical languages indeed have an LLVM-based compiler, such that building on top of that toolchain permits to integrate with those languages. And specifically, it allows to use and link in libraries or backends written in these languages. Being able to connect and integrate with classical tools like this is really important, especially as we're still working towards developing applications, because ultimately we don't spend the majority of our time actually executing programs on quantum hardware. The majority of our time we spend looking at different options, implementing algorithms in different ways to determine how to best do this. Currently, for example, we're collaborating with Pacific Northwest National Laboratory to connect to a GPU-based backend for simulation purposes. So to summarize, QIR defines how to represent quantum programs within the LLVM IR. It does not require an extension or modification of LLVM such that all the standard tools will work. Most importantly, QIR is not specific to Q# or the tools that we build. Any programming languages for gate-based quantum computing can be compiled into QIR. And similarly, it is hardware agnostic, such that it does not require a particular quantum instruction set or a gate set. To define the quantum instruction set or the gate set is really left up to the target environment. In Q#, for example, it is expressed merely as a Q# library. So QIR thus defines a foundation for developing optimization passes and code transformations that can be shared across different languages and backends, and facilitates integration between different frameworks. For example, we're currently collaborating with Oak Ridge National Laboratory to enable an integration with the XACC quantum programming framework. QIR allows for arbitrary interactions between classical and quantum computations. Now, since this is not necessarily supported by all backends, you might be wondering how we make it work to execute that format on the current quantum hardware. For that, we define different profiles. So that's subset of the QIR that reflect the capabilities supported by these backends. And with that, we can do cool things, like, for example, executing such a repeat until success-based algorithm on today's quantum hardware. So why is this so interesting? Well, what we can do is we can do classical computations, like whether or not to continue this loop based on measurement outcomes while other qubits remain live. So that is, while the quantum state remains coherent. And perhaps even more importantly, we can express this in a fairly natural way, such that it's easy to run the same routine for a different number of iterations and for different inputs. So why is QIR important? Quantum computing is still in its infancy. The quantum computing community is tiny compared to the broad computing and programming community. Computing has grown in ways that would have been impossible to predict in the early days. If we want to emulate and accelerate a similar progression for quantum computing over the next couple of decades, not only do we need to take full advantage of the classical tools and resources at our disposal, but we also need to leverage the insights into how computing itself has evolved over the course of more than half a century. We have the tremendous advantage here of having the hindsight into what the essential success factors were that made that growth possible. In the coming years, we expect there to be exciting advances in how classical and quantum computations can interact at the hardware level. With QIR, we provide a foundation for developing software frameworks that can target today's devices and more powerful systems in the future. And with that, I'd like to thank you very much. If I got you curious, please visit our dev blog or the Q# language repository given in the links on the slide to learn more about the quantum intermediate representation and how to contribute and collaborate.
Okay, so thank you, Bettina, for your nice talk. I have a question for you. So for this quantum programming, so it's if I understand, for all these gate operations, like if I write a quantum circuit, the gates by itself they are quantum, but if I do the instruction for the gates, I do first this gate and then that gate, this kind of instruction is still classic. So I'm wondering, like, for this quantum programming, so what do you consider was the unique for quantum programming different from classical programming? So what kind of thing make them uniquely different from the classical case when you write programming?
Mm-hmm. Yeah, I think where quantum is very unique is really, from a compiler perspective at least, where what kind of things are expensive and what we optimize for, really. So classical computing has evolved in a way that there are usually a lot of individual optimization passes that each one is a rather simple approach. For example, it's a very first order approximation to evaluate something like a cost function usually, but then hundreds of passes that all play together are combined during compilation. For quantum, it's not entirely clear that this is how it's ultimately going to evolve. I think it's perfectly possible that we want to do a very good job at optimizing exactly certain things and take far less care to optimize the same thing we would classically. But that doesn't mean we can't leverage some of the same tooling, basically, that we already have at our disposal. It just means that we adapt kind of the cost metrics that we look at and how we do those optimizations.
Okay, thank you. So I have another question for this Q-sharp or this QIR. Do you consider this as a high-level language or as a low-level language? So in particular, for instance, so whether do you consider any like time delay between operations? So if I do quantum gates, it's probably okay. But if I do also quantum error correction to fault tolerance, I probably need to consider the time constraint of each operations and whether I can do real-time feedback, for instance. So do you take that into account when you write this kind of language or when you do this design?
Mm-hmm. So I think as quantum computing, starts to mature a little bit, we also start to better distinguish kind of what the functionalities need to be for different pieces in our stack, so to speak. And while Q-sharp itself, in a way, is definitely a high-level language, aside from that it does deal with individual qubits, like I think pretty much all quantum programming languages. The fundamental idea for us is that we also build a stack below that really is very extensible. So for example, the Q-sharp compiler has a mechanism to just plug in different passes. And we also intend to have similar mechanisms throughout the lower layers of the stack, with the idea that if for whatever research purposes or other reasons, there's a need to have more access or more control to some of the hardware-specific capabilities, so to speak, like pulse sequences and durations of thereof, then that would be integrated easily, basically, into this tool chain rather than exposed through the language necessarily.
Okay, so thank you for your nice talk, and thank you again for your these helpful answers. I guess we probably need to move on.